Welcome to the Padhai Kar Lo JEE Preparation channel. You can practice more problems on this exact topic on our Padhai Kar Lo Android app, link in the description below, or on our website padhaikarlo.com. Today's topic is power factor and the reactance difference in AC circuits, a genuinely high-yield numerical topic within alternating current. Let's begin. In a pure resistor, voltage and current oscillate exactly in phase, so all the electrical power delivered is genuinely, fully consumed. But in a circuit containing inductors or capacitors, current and voltage develop a phase difference, phi, between them, and power factor is defined as cosine or that phase angle, phi. Power factor tells you exactly what fraction of the apparent power Vrms times Irms is actually converted into real, useful average power equals Vrms, Irms, cosine phi. A power factor 1 phi equals 0 means a purely resistive circuit, all supplied power is genuinely used, while a power factor, or 0, phi equals 90 degrees means a purely reactive circuit, inductor or capacitor, alone, where average power delivered is genuinely, exactly 0 since energy simply oscillates back and forth without any net consumption. In a series RLC circuit, the phase angle phi is found directly from tan phi equals XL minus XC, all divided by R, where XL is inductive reactance, omega L, XC is capacitive reactance, 1 over omega C, and R is resistance. This specific quantity, XL minus XC, the reactance difference, is exactly what determines whether the circuit behaves more inductively or more capacitively overall. When XL is greater than XC, the circuit is net inductive, and current genuinely lags voltage. When XC is greater than XL, the circuit is net capacitive, and current genuinely leads voltage. And when XL exactly equals XC, the reactances cancel completely. Phi becomes exactly 0, power factor becomes exactly 1, and the circuit is genuinely at resonance. Impedance Z, the total effective opposition to current flow, is found from Z squared equals R squared plus the quantity XL minus XC squared, and power factor can equivalently be written as R over Z, a form that's often more directly convenient for quick numerical calculation. For a typical G power factor numerical, first calculate XL and XC separately from the given angular frequency, then find their difference, XL minus XC. Next, calculate impedance Z using the formula involving R and this reactance difference, and finally compute power factor as either cosine phi, or the equivalent, often faster, R over Z, a common trap. Students sometimes forget that power factor is always a genuinely positive, dimensionless number, between 0 and 1 regardless of whether the circuit is net inductive or net capacitive, since cosine of a negative angle equals cosine of the corresponding positive angle. The sign or the reactance difference tells you the direction of the phase shift, lagging, or leading, but not the power factor's own magnitude. Also remember that what less current that transfers genuinely 0 net average power flows specifically when the circuit is purely reactive, R equals 0. This is exactly why power transmission systems are always deliberately designed to keep power factor as close to 1 as practically possible, minimizing wasted reactive current for a given amount of genuinely useful delivered power. Let's recap. Power factor, cosine phi, tells you what fraction of apparent power is actually used. Average power equals Vrms Irms cosine phi. The reactance difference XL minus XC determines the phase angle through tan phi, with XL greater than XC giving a net inductive, lagging circuit, and resonance occurring when they're exactly equal. Power factor equals R over Z, always a positive number, between 0 and 1, and power systems are designed to keep it close to 1 to minimize wasted reactive, wattless current. That's power factor and reactance difference in AC circuits. Keep the R over Z shortcut sharp. It's the fastest path through most G power factor numericals. If this video helped, please like it and subscribe to Padhai Kar Lo for more JEE preparation content just like this. See you in the next one.